is we're going to be looking at finishing chapter 3 probably by Monday, and then we'll probably make some good, I think, hopefully the first 2 sections of chapter 4 on Wednesday, and we'll do an exam after chapter 3 and after chapter 3 and 4, and I think we should be all right on the schedule. If there's anything that I think we need to maybe speed up on, I'll let you know. But I think we're doing, if we stick to that, I think we should be all right. So the next section, we're looking at 3.8, and we're doing inverse functions. Now, we've seen how inverse functions work before, and if f and f inverse are, well, they're truly inverses, we're going to have the following property. So if we have an inverse relationship here between these 2 functions, then switch it up a little bit here. Do it this way. Well, then this is what's going to be true. If these have an inverse relationship between them, then f inverse of f of x will just reduce down to x. Then f of inverse of f will reduce to x. So in other words, we take the composition with f of x going inside the f inverse, we get x. If we compose f of inverse inside f, we're also going to get x. Now these both have to hold true. They'll both hold true if these are in fact inverses of each other. Both of these are going to hold true. So what we're going to do is this. We want to try to figure out the derivative of an inverse function. So what we can do, let's stick with this. We're going to find d dx of f inverse of x. And what we're going to rely heavily on today is the chain rule. So we have that f of f inverse is equal to x. And again, this has to be true, and this would also be true as well. We're going to take the derivative of both sides. Now, if we take the derivative of the right side, the derivative of x with respect to x is just 1. But on this side, we've got to do the chain rule. So the chain rule is, we're going to use that outside inside rule. We'll take the derivative of the outside function, leaving the inside function alone as long as it's on the inside. And then we're going to multiply by the derivative of that inside function. Now what we can do, we'll divide both sides by f prime of f inverse. So this will cancel. And we're going to get that d dx of f inverse is 1 over f prime f inverse of x. So that's going to be our answer. So any questions about that? All right. So let me do an example. And this is going to be an example that's going to help us out a pretty good deal today. So we're going to try to figure out what the derivative is for the natural log of x. Now, we do have the derivative for e to the x. The derivative for e to the x is just e to the x. Doesn't change. So to figure out the derivative of the f inverse, which is ln of x, well, this is going to be the derivative of ln of x. And for us, we're going to have this. So questions about this. So what we have is e to, usually e to the x here. And so f prime would be f prime of x. So we have f prime of e to the x is just e to the x. The derivative of e to the x is e to the x. But then we're going to do a composition. We're going to take the composition of this derivative with the inverse function. So here's our f prime. We take the composition of our inverse function. We're going to put our inverse function up here. So it might help maybe if I take a step back. I'm going to f inverse our exponent. And that's why we're seeing e to the natural log of x. Now, e to the x and natural log of x are actually inverse functions of each other. So the base here is going to cancel, and this is a log base e. So keeping in mind that ln of x is log base e of x, this is going to imply that 1 over e to the natural log of x is 1 over e to the log base e of x. These are going to cancel. The base of an exponent, or the base of an exponential expression, matches the base of a logarithmic expression. They're going to cancel. We're going to get 1 over x. So in short, what we find out is d dx ln of x is 1 over x. Now, questions about that? Now, what you're going to start seeing, and if you haven't seen it already, you have this expressed in terms of u. So what we'll oftentimes see is d dx of the natural log of u is equal to 1 over u times du dx. You'll see it written like this in terms of the chain rule. And this is just to emphasize the significance of the chain rule. So the derivative of the natural log of u, well, it's going to be 1 over u, just like we have 1 over x. But then we multiply by the derivative of u with respect to x, again, because of that chain rule. So this part right here you're going to see this a lot. So again, that's just because of the importance of the chain rule. So questions about that? All right. So we're going to take a look at another one of these. Now, with that derivative of e to the x, the derivative of e to the x is just e to the x. Or put another way, you could also see it this way. Again, using our chain rule. But what happens if we have a base other than e? So let's say we're going to take a look at a to the x. I'll just make a note here. We want to make sure our a is greater than 0. So to do this one, we're going to kind of come up with a little trick. Note, we can rewrite a to the x as e to the natural log, because again, this is a log base e, so the e here is a base for an exponential expression, and the logarithm expression, they would cancel out. So we can rewrite it like this. And you have a logarithm of any kind with your, or of your proper base. And then you have a exponent expression. We can drop the exponent down like so. It's that rule for the powers. So this is going to be a trick that we're going to use here for a little bit. It's really helpful. So now we're going to compute the derivative of a to the x. Well, to do this, we're going to rewrite it as the derivative e x natural log of a. Now we're going to let u equal x natural log of a. And the thing to keep in mind here, natural log of a, that's just some kind of number. So this is a number times x. It's not really any different than 3x, for example. So now we can rewrite this is d dx of e to the u, and then we're going to need well, as we calculate e to the u, it's going to be e to the u times du dx. Questions about that? Or I might slip in another step here. Let me bring this back into play. And there we go. So what we know is that taking the derivative of u with respect to x is going to be d dx, x natural log of a. And again, natural log of a is just going to be some number. It could be an integer, it could be a rational number, it could be an irrational number. But whatever it is, it's a constant. And a constant times x, when we take the derivative of a constant times x, we're just left with that constant. So this means e to the u du dx will be e to the x natural log of a times the natural log of a. And we can put this other one a little bit back together. And again, the e and the natural log will cancel out. And we're going to be left with a to the x natural log of a. So what that means, the derivative of a to the x, it's a to the x natural log of a, or d dx, a to the u will be a to the u natural log of a times du dx. Questions about that? And again, you want your a greater than 0. It's going to be a requirement of that natural log. So that's how we can come up with the derivative of a to the x. Now, if we think about this, let's take a look at our derivative of e to the x again. Well, according to our formula, it'll be e to the x times the natural log of e, or e to the x. And then the natural log of e, well, again, keep in mind, you have a logarithm, base e, of the number e itself. So you have a base matching a base, just going to cancel. And you can say this is a 1 up here. So that's going to leave us e to the x times that 1, or e to the x. Questions about that? So even with this new formula, it's still going to hold up for e to the x. We get the same result. So we have consistency here. All right. So let's take a look at this. Now we looked at the derivative of ln of x. Derivative of the ln of x. That was 1 over x. Or, put another way, we saw this earlier. So what if we want something a little more generic? Like, let's say, for example, the derivative of respect to x of the log base a of x. So let's say we want to figure this out. Well, what we can do is use a rule for logarithms that says this. The log base a of x, you can rewrite it as logarithm base e of x over logarithm base e of a. Now, we don't have to use natural log. We could have used log base 10 and log base 10, log base 3, log base 3, but we already know how to work with natural log, at least when it comes to taking derivatives. So we'll go with natural log. So now, the derivative of log base a of x, this is now the derivative of the natural log of x over the natural log of a. Now, natural log of a, that's just a constant, some constant number. So we can pull this out. We can treat this as the derivative of 1 over natural log of a times the natural log of x. And just like with limits, we can pull the constant through the limit, we can pull the constant through the derivative. So this will become 1 over the natural log of a d dx of the natural log of x. Now we know what the derivative of the natural log of x is. This is 1 over the natural log of a times 1 over x. Or put another way, it's going to be 1 over x, natural log of a. And again, we want x greater than 0. Oh, sorry, a greater than 0. So any questions about that? All right. So what this basically says is this. d dx log base a of x is ln of x 1 over x ln of a. Or, incorporating the chain rule, one over u natural log of a du dx. questions about that? All right. So we're going to put something together here. Hopefully this makes things a little easier. Let's see. So let's say we got something like this, and this is an example from the text. You can see it on page 172. But you could use the quotient rule on this, that would be fine. But we're going to try something else. And this is sort of a clever trick. We'll start out with the function as presented. Now, there's a key thing here. X has to be greater than or equal to 1. So I'm going to division by 0 here. And another issue, too, is we don't want this to become possibly negative. So I do want to mention that. What we're going to do is we're going to take the logarithm of both sides. What that's going to mean, though, for logarithms, we can't take the logarithm, whether it's a log base a or a natural logarithm, we can't take the logarithm as something negative. So what we're going to do here is we need x to be greater than 1, so this doesn't come out to be negative. So this is a key point in this problem. Because if this is negative, we won't be able to take the logarithm of it, and we're actually going to do that. So what we're going to do, we'll take the natural log of y on this side, and then we have the natural log of this whole thing. Now, what this does, and it's been a little bit since we've looked at this, we want to think back to our logarithm properties. The logarithm of a product will be the sum of logarithms. The logarithm of a quotient is going to be the difference of logarithms. So we're going to get this. And this is where, again, we need to make sure this is going to be positive. It's only going to be positive if x is bigger than 1. So logarithm of a quotient, difference of the logarithms. Now logarithm of a product, sum of the logarithms. And to write the minus natural log of x minus 1 instead of here, just running out of space. And then we've got another property we could introduce. You've got a logarithm, could be natural, could be log base 10. We have something here with an exponent. Exponent is going to hop down. So now you might be tempted to do something with this, but you can't. The logarithm of a sum, we're just stuck with it. It's only when you have the logarithm of a product can we break it up to the logarithm of a sum using our logarithm rules. And so this we're just going to leave alone. So, okay, we've broken everything up. But how does this help? Bear with me. What we'll do next is take the derivative of both sides. So we'll take the derivative with respect to x of the natural log of y, and the derivative with respect to x of this whole thing. Natural log x squared plus 1 plus 1/2 natural log x plus 3 minus natural log x minus 1. Take the derivative of both sides. Now, recall what the derivative of a natural logarithm is. It's 1 over whatever's here. But let's keep in mind, recall y is a function of x. So what that's going to mean, or maybe it's a little easier to see it this way, just keep this in mind. And this might be a terrible use of notation, but you could think of y as y of x. I'll be honest, I almost never see anybody write something like that. So, but I think here we could take a risk. And this is why, no pun intended. We're going to use that rule, the chain rule here. This is a function of x. So what this means, and think back to implicit differentiation, this will be 1 over y, again, derivative of a natural log, times, instead of du dx, it's going to be dy dx, because we have a y instead of a u. Now this derivative of sums and differences will be the sums and differences of the derivative. So you have d dx, natural log of x squared plus 2, plus d dx of 1/2 natural log x plus 3 minus d dx of the natural log x minus 1. So that being the case, we have functions inside this natural log function. So this is going to act like a u. So we're going to get 1 over u times du dx. So we get 1 over y dy dx. And so this will be 1 over x squared plus 2 times the derivative of x squared plus 2. And again, this is the chain rule. The derivative of the outer function is going to be 1 over whatever's on the inside of this natural log function. And because it's a natural log, that's why it's 1 over. If this was a different kind of function, we would be arranging things differently. But because it's a natural log, the derivative of natural log is 1 over whatever's on the inside here. So that's what we got here. And then by the chain rule, we multiply by the derivative of what's on the inside. The same thing here. Now the constant will always pass out through the derivative. So it'll pass on through. And so the derivative of natural log of x plus 3, well, that's 1 over x plus 3 And by the chain rule, take the derivative of what's on the inside and multiply it to everything else. Oh, let me see, did I write it wrong? Squared plus 2. Oh, was it x squared plus 1? Let me see. You're right, you're right. Ooh. It is x squared plus 1, sorry. Thank you very much. Thank you very much. Yeah, that's what it is. Yeah, this 2, it should be a 1 here. It didn't magically become a 2. Yeah, thank you for catching that. Oh, and that means this is going to be 1 also. Okay, I think we're okay. One last term, the minus. So again, 1 over x minus 1 times the derivative x minus 1. So questions about that? I admit there's a lot of steps here. And in theory, well, it's an alternative to say using the quotient rule. I'll let you decide if you think this is an easier way to go about things than the quotient rule. And actually for this one, you would get the quotient rule and the product rule thrown in. So again, I'll let you decide which one you think's better. So this is what we've got. We need to take the derivatives of this, this, and this. So you have 1 over y dy dx. 1 over x squared plus 1 times the derivative of x squared plus 1, derivative of x squared, 2x. Derivative of 1, 0. So this will be 2x plus 0, or just 2x. Plus 1/2 times x plus 3 times derivative of x plus 3, derivative of x will be 1. Derivative of 3 is 0. 1 plus 0 is 1. So we've got 1. So we got 1 over x minus 1. Derivative of x minus 1. Well, derivative of x again is 1. Derivative of 1 is 0. 1 minus 0 is 1. So we've got that. So putting this all together, 1 over y dy dx, that's going to be 2x over x squared plus 1 plus, we're going to distribute the 2 through the terms of this denominator, give us 2x plus 6. And then finally we subtract 1 over x minus 1. So this is where that part from implicit differentiation comes in from the last section. We want to find dy dx. And so what we can do is solve for dy dx. So we'll multiply both sides by y. So y's are going to cancel on this left side. Multiplying the whole side by y, so we have y times 2x x squared plus 1 plus 1 over 2x plus 6 minus 1 over x minus 1. Questions about that? Well, there's one step left. We do know what y is. Y was the original function we were working with. So, what that means is that dy dx is going to be in terms of this y. So while you're writing that down, I'm in search of pins. Ah, well, that answers that. So dy dx, I'll squeeze this in here. X squared plus 1. X plus 3 to the 1/2 over x minus 1 times 2x x squared plus 1 plus 1 over 2x plus 6 minus 1 over x minus 1. Double check all right. Whew. And that's going to be your answer. Now, I'll admit, there's a lot of steps in that problem. And some of those steps, as you feel more comfortable doing derivatives, you can skip some of them and you just say, okay, this is the derivative of that. And you can tighten up the work a little bit. The question is it easier to find this derivative using this method or applying the quotient rule and then ultimately the product rule as well on something like this? So again, I'll let you make that decision. All right. I'll dig for some more things to test here. The hope being that I might have been too zealous in removing some of them. So what we're going to look at is a stronger verification of the derivative of x to a power. We're going to use this trick. So starting out with this, we can write it as e to the natural log of x to the n. In e and natural log would normally cancel out. And we'll call this e to the n natural log of x. Again, that exponent is going to hop on down. So this is for any x greater than 0 and any real number. Yeah. So this is going to be the added bonus. Oh, all right. So what we'll do, d dx, x to the n, will be d dx e natural log x to the n, or d dx e m ln of x. And again, ultimately, you're going to be taking the derivative of ln of x through the chain rule, and we know what that derivative is. So we're going to let u be in ln of x. So what this means is that the derivative of e in ln of x is going to be the derivative of e to the u. And then using our chain rule, well, derivative of e to the u is just e to the u. And here comes that chain rule, du dx. And in du dx, well, again, here's u. N is a constant. We're taking the derivative of the natural log of x. Du dx. That's going to be d dx of n, natural log of x. Constant n is going to pass through. We'll get n times 1 over x, or n over x. So that being the case, e to the u du dx is going to be e to the u times n over x. So now let's bring back u. Or u was in ln of x. Or e to the natural log of x to the n over x. Or, again, these will cancel. We'll get x to the n times n over x, which will be n x to the n over x. Or n x to the n minus 1. Because we're dividing by an x, this is x to the n. You could think of this as x to the 1. And so we're going to get x to the n minus 1. So any questions about that? All right. I just want to make a note. This works for x less than or equal to 0 when the derivative or x to the n or n x to the n minus n all exist. So the note they have in the text, because we did this originally for x greater than 0. So any questions about that? All right. So let me show you one more, kind of a fun one, I think. Let's say we got to take the derivative of this. So In this case, we're going to use that same trick. X to the x equals e to the natural log of x to the x, or e x natural log of x. So again, what we can do, df dx will be the derivative of e x natural log of x, or the derivative of d dx, and we'll let this be e to the u, or u is x ln of x. And so this will be e to the u times du dx. So you got to compute du dx. Well, this is going to be a product rule. So d dx, x ln of x. Well, we're going to break this up into two functions, f of x, g of x. So we're going to get f of x prime times g of x plus f of x times g of x prime. That's going to be our product rule. So derivative of x is 1 times ln of x plus x times, well, the derivative of natural log of x is 1 over x. So we get natural log of x plus 1. So now we go back to this. E to the u du dx. Well, now we know what we've got. So e to the u, e to the x, ln of x, times ln of x plus 1 or e to the ln x to the x, ln of x plus 1 or x to the x, ln of x plus 1. So again, using that e with a logarithm in it, natural logarithm, that's a neat trick. You can use that quite a bit. Questions about that? All right. So I might go in a little overtime today. I'm going to jump into inverse trigonometric functions. If you want to review these, you can see it on page 45. I'm just going to go over some of the derivations of where these come from, sort of introduce these formulas. And I'm probably going to go over time a bit, so I'm recording the lecture. So if you have to miss 10 minutes at the end, it will be recorded. It'll be available. So first off, inverse trig functions. And these are for the derivatives. So let's say we want to do this. The derivative of the sine inverse of x. How do we find this? Well, we're going to use that formula we derived earlier today. We have the derivative of an inverse. So d dx f inverse is 1 over f prime of f inverse. So we're going to use this formula. Now, we need to know f prime. So we've got f inverse. So f is going to be sine x, which implies that f prime of x is the cosine of x. So what this means, the derivative of sine inverse is going to be f prime, or in this case, cosine of that inverse function that we're trying to take the derivative of. Sine inverse of x. So questions about that? All right. Now we're going to use those skills about how to work with inverse trig functions. Ooh, still works. So let's think about the cosine of the sine inverse of x. Well, start with sine inverse. Sine inverse. An inverse function is an angle. So this is going to be angle theta. Or put another way, x is going to be the sine of theta. So cosine before we do that, we're going to use this fact to construct a triangle. So here's our theta. Here's our right angle. So what this says is this: the sine of theta is x. It's actually x over 1. So sine of theta, that's x over 1. This is our opposite. And this right here, that's our hypotenuse. So that means if we take theta, the opposite is going to be x. And sine is opposite over hypotenuse, so that means the hypotenuse is going to be 1. So this means if we solve for this side, well, we're going to get 1 squared. This is the adjacent side. So 1 squared plus x squared plus a squared, using your Pythagorean theorem. Solving for a, we'll get 1 minus x squared, square root that, is going to give you your a. So a, square root of 1 minus x squared. So questions about that? So what we do, sine inverse is an angle. So if the sine inverse of x is theta, that means x is the sine of theta. This is our definitions for an inverse. That being said, since sine of theta is x, or x over 1, we can construct a triangle where the opposite must be x and the hypotenuse must be 1. Then we solve for the missing side using the Pythagorean theorem. So hypotenuse squared is side squared plus side squared. We know this is x. This is the one we're looking for. Then we solve for it, and that tells us this. So we've completed this triangle using that information. So now we got to figure out this. The cosine of the sine inverse of x, we're remember, this is theta. So this is the cosine of theta. We're still using the same triangle. Nothing's changed. So the cosine of theta, which is adjacent over hypotenuse, well, that's the square root of 1 minus x squared over 1. Or square root 1 minus x squared. So again, what we're doing, cosine of sine inverse, inverse functions are angles, they're thetas. So that's really the cosine of theta. So we go back to this triangle that we derived, and we look for the cosine of theta, which is adjacent over hypotenuse. And so this is what we're going to get. Cosine of sine inverse is equal to that. So going back to our derivative now, the derivative of sine inverse of x was 1 over cosine sine inverse of x, or 1 over this, square root 1 minus x squared. Or putting it another way, du dx sine inverse of u will be 1 over square root 1 minus u squared times du dx. Questions about that? All right. So that being the case, what about tangent? Let's do tangent. So for tangent, again, same thing. We're going to take d dx f prime of x 1 over, oh, I'm sorry, f inverse. Ooh. 1 over f prime of f inverse. And so that's going to give us 1 over. Now, before I do that, note that we need the derivative for tangent of x. So f of x is going to be tangent of x. So f inverse is tan inverse, f of x is going to be tangent of x. So the derivative of tangent of x is secant square root of x. And I'm going to make a little observation here. Recall secant square root of x is 1 plus tangent square root of x. Check something real quick there. Hold on, pardon me 1 second. Yeah, that's fine. That's fine. All right. So that being the case, the derivative of tangent inverse of x is going to be equal to 1 over secant squared. So that's the derivative of tangent, secant squared. And then the inverse is tangent inverse. Of x. So we're going to do a little trick here. We're going to use that identity. So this will be equal to 1 over 1 plus tangent squared of tangent inverse of x. So again, we can treat tangent x like it's an angle theta. And so in that case, because we can treat it like an angle theta, this is like secant squared theta, which is going to be equal to 1 plus tangent squared of theta. And to make things a little more understandable, we can rewrite this as 1 over 1 plus tangent inverse of x. Because when you square a trig function like this, this is what it really means. Now to save time, because I know we're kind of eating up time here, tangent inverse, they're going to cancel out, they're going to give you x. Now you do want to be a little careful with how you cancel these. I can post something about, just want to be careful how you cancel your inverse functions with your regular trig functions. You do want to mind some issues with domain. If you're not sure, you can always build triangles out of these if you're dealing with x, but for the sake of time, we'll just cancel them out. But there are some problems in this section where you are working with combinations of inverse functions and non-inverse functions, and you don't want to be too freewheeling with the cancellation. But I can post something later just for the sake of time. So this will be 1 plus x squared. So what we get is this. d dx tangent inverse of x is 1 over 1 plus x squared, or d dx tangent inverse of u is 1 over 1 plus u squared times du dx. Questions about that? Oh, don't want to leave this one out either. So let's see, I think we have time for secant inverse. So any questions about that? I think it's about time to try another bin. Ooh, it still works. All right. So d dx secant inverse of x. And what's kind of neat about these derivations is you're learning some clever tricks that can help later on in your calculus. So this is what we're going to do here. If y is secant inverse of x, that means the secant of y gave us x. So now we're going to take the derivative of both sides. So this means we're going to get some chain rule and some implicit differentiation, which is never a bad thing. Well, perhaps I shouldn't say never, but it can be a fun thing. So once again, derivative with respect to x of x dash of 1. And this one, we're going to use the chain rule. Y is a function of x. Using that notation there. So what we'll get is Well, the derivative of the secant of y, well, derivative of secant is secant y tangent y. And then, because of the chain rule, dy dx. So we'll divide by secant y tangent y, solving for our derivative, and dy dx. And keep in mind, y is originally secant inverse. Dy dx is 1 over secant y tangent y. So we just got to do something with this. Well, keep in mind, since y is the secant inverse of x, well, as we just saw recently, that means secant y is just equal to x. So that's not too bad. Now, it's a little trickier for tangent. Since 1 plus tangent squared, y would be equal to secant squared y. Well, that means tangent squared y is secant squared y minus 1. And we're going to take the square root. So that means tangent y is plus or minus secant squared y minus 1. Well, good news. We do know what secant y is. It's x. So tangent y is plus or minus x squared minus 1. So we got these two substitutions. So bringing this all together, dy dx is going to be x square root x squared minus 1. We're going to have a plus or minus attached to this. So what should we do here? Well, we're going to make an observation. We're going to try to resolve the plus or minus. And the way we're going to do it is this. Let's take a look at the graph for secant inverse. So we're going to get something like this. We're going to get something like this. So this is our graph of y is secant inverse of x. So we want to notice something here. The derivatives are always positive. So when we choose to attach a plus or a minus to this derivative, because this means we got to make a choice. So if we think about the derivatives, they're tangent line. So the tangent line is going to be, say here, this is a positive slope line. Or you have a tangent line here, that's also a positive slope line. So that means the derivatives for this function they're going to be positive. So that means we need this. We need the plus on this part for x greater than 1. Why is this? Well, when x is greater than 1, we're talking about this part of the function. And again, the derivative is positive. So that means if you look at this part of the domain, this is going to be positive. Now this is also going to be positive. We want to keep this positive. We don't want to accidentally put the minus on here. So we'll keep this positive by giving it the plus. But let's take a look at for x less than negative 1. Well, when x is less than negative 1, x is, of course, negative. So now this is still going to be positive. We're going to square x and then positive number minus 1. It's going to be positive. Again, x is going to be less than negative 1, so like negative 1.2. So you're going to get 1.2 squared, which is going to be bigger than 1. And that bigger number is going to subtract 1. You're going to get a positive result. This is positive, but this is going to be negative. So let's give this one the negative sign. When x is less than negative 1. So the negative and the negative will keep this derivative positive. So that being the case, we can simplify this another way. Here we want to keep x positive. We want to make negative x negative. Oh, I'm sorry, positive. Ooh, getting a little, I want to be careful there with the consistencies. Words. So basically, we want to make this x positive, whether it's positive or whether it's negative. So that means we can replace the plus and minus and x with the absolute value of x. We can do that. Because all we're doing is using the plus and minus to keep this positive and to make this negative into a positive. Well, that's what absolute value does. It just keeps things positive or turns the negatives into a positive. So this is what we get. So after our long journey, we get 1 over the absolute value of x, square root x squared minus 1, or we'll get, here I'll remember y is secant inverse, or d dx secant inverse of u will be 1 over absolute value of u square root u squared minus 1 times du dx. And that's the last of the real heavy lifting ones. So I just got just one little bit of quick notes here, and then that's going to be, I'm just going to show you one sort of quick derivation and then give you the other two trig functions that we're leaving out. and then we're going to be done. So I think we'll go over by about 10 minutes. Well, there's some neat algebra tricks in here. They're kind of cool. So for cosine inverse, good news about this one. We had some inverse trig identities at the beginning of the course. This one. And at the time, it probably looked a little doubtful what we're going to use this for. But what we're going to use it for is we can make a substitution. It's going to make our job a lot easier. So this will be 0 minus the derivative of the sine inverse of x. And what we're going to get is negative 1 over square root 1 minus x squared. That means for cosine inverse of minus 1 over square root 1 minus x squared, or d dx cosine inverse of u minus 1 over square root 1 minus u squared du dx. Questions about that? So likewise, we're going to get this. So cotangent it's pi over 2. Oh, sorry, I'll put the derivative. Minus tangent inverse of x. For cosecant, secant inverse of x. So using the same technique, what we're going to get is the derivative of cotangent inverse of x is minus 1 over x squared plus 2. And there's a requirement here. Absolute value of x needs to be greater than 1. Or d dx cotangent inverse of u is minus 1 over u squared plus 2. Wait. Plus 1, I'm sorry, plus 1. Seem to be putting 2's everywhere today. Du dx. And then the last one, and that's going to be it. Derivative cosecant inverse of x. This will be negative 1 absolute value of x So it picks up a negative again. Let's see, x squared minus 1. And again, for the absolute value of x greater than 1. Or d dx cosecant inverse of u will be minus 1 over absolute value of u x over u squared minus 1 du dx. And so those are the inverse trig functions. That's how we get those. So that's going to be it. So that takes us through section 3.9. We have 3.10, 3.11 to do, and then we're done. I'll post something about this, a little bit of a trig review, like the first, well, it's the first 11 questions, at least in the textbook homework. You want to be a little careful. You want to watch some of your domains here with your inverse trig functions, and I'll post something about that later. But that's going to be it. So if you have any questions, let me know, and we'll just go from there. And they're going to have you do some limits with these two, actually. The thing with the limits on the homeworks, it helps to look at a graph. Look at a graph of your inverse trig function, and then compute your limits. And so this kind of gives you a chance to familiarize these limit questions. It lets you familiarize with the domains of the inverse trig functions. So like, what does cosine inverse if you try to take the limit as x gets close to +1? And it's just a way to familiarize the behavior of these functions along their domain. So if you're a little concerned about those limits, take a look at the graphs of these functions. That'll definitely help. So that's it for today. Any questions, let me know. Other than that, have a wonderful weekend. I'll take a look at those quizzes, and I'll put out information for the next quiz on Monday. We're going to be quizzing for the rest of the semester. So other than that, have a wonderful day. Oh, I mean,